Hi, my name is Jim. Welcome to part 2. We're going to discuss signals and noise with regard to what it actually looks like in electronic equipment. Now, to model this, I just made up a voltage divider here of 1K over 1K, and if I were to find the power associated with Vn, it would be some number, and if I were to find the power associated with Vout, where the voltage is cut in half, the power would be 25%. So by cutting the voltage in half, the power drops to 1/4. Now if I go down and take a look at that here, in the log domain, I see that 10 times the log of 0.25 is equal to -6 dB. So if you have an antenna on your house and you're wiring it into a room, and you do not have a mask-mounted preamplifier, you could lose 6 dB in the cable. If you have a cable TV system with a splitter with 4 spigots, each spigot is down by 6 dB plus a little more. There's additional loss in there. So a little model here represents some real-world stuff. And the bad thing about S to N ratios is once they're compromised, it's hard to get them back, if not impossible. So we're going to start out with a signal here. I'm going to call it Vn, and then I'm going to compare it to Vn over 2, and what I see is that the voltage would decrease by 6 dB. So it would be 1/4 the power. A 3 dB drop in power would be, the voltage would drop to 50% and the power would drop 6 dB. So anyway, at this point we're looking at Vn over 2, and what we've kind of see is that the signal level is now closer to the noise floor. You might be thinking, well, that's okay, I'm just going to go through and add a ×2 amplifier and fix it, and that's what we're going to look at doing here. So I lost some voltage and compromised my signal to noise ratio. When I say lost voltage, I also lost signal power too. So here's the same circuit, but I got a ×2 amplifier on the tail of it here, and what my desire here is to get back to our original voltage Vn, and hopefully that will restore the signal to noise ratio. And what I find is when I put the divider in, I dropped 6 dB as before, and then when I put the amplifier in, it increased it 6 dB. But it also increased the noise floor by 6 dB. So any gain I put downstream from this can't help me. Further, the signal to noise ratio here is slightly worse than the signal to noise ratio here, because this amplifier is contributing noise to it. So it's a little bit worse. So if you're designing anything, it's always a good idea to keep noise in mind during the design process instead of having to clean it up after you design something. And with regard to PC board layout, I've got a lot of bad examples that occurred with me over the years. So let's take a look at the equation for the above. And we have an amplifier, and that amplifier is not perfect. It has a gain, power gain, and a noise voltage contribution here, and this is the signal to noise input, and it goes through this amplifier and it is degraded a little bit, and then the output would be the gain of the amplifier times the signal, which we would expect, divided by the gain of the amplifier times the noise, which we would also expect, plus the noise component of the amplifier itself. Now that's in the denominator. So what that means is that the S out to N out ratio is going to be less than the S in the noise in ratio. So it's kind of backward logic when you think about amplifying something. Yeah, the output's going to be greater, but in the case of noise, it's worse. Signal to noise ratio degrades with every device it goes through. Okay, it's quantified well by Friss in his formula, and what this is about is cascaded stages. And here we have an antenna, symbol for an antenna, and we're going through 3 gain stages. And the way this works out is that we have our noise factor here from the first amplifier, and F2 is the noise factor from the second, and so forth. And this stage is named A1, which is also the gain, and stage A2, which is also the gain. And if we go to look at the total noise factor coming out of the amplifier here, we find that it's F1 all by itself plus F2 minus F1 divided by the gain of A1. So now the signal's higher going into A2, and therefore the contribution of noise of A2 isn't as damaging. And then if we take a look at F3, that's even better from its standpoint of contributing. Noise factor minus 1 divided by the concatenated gain of these two, so the signal going into him is really large. Therefore, his noise factor, F3, doesn't affect the signal as much as the gain of stage 2 or stage 1. Now what this means practically, if you need a good noise factor overall, is you want to spend your money on the very first stage. With low noise components, you pay super attention to anything that can cause trouble. Now on DirecTV dishes, the actual low noise amplifier or low noise block converter is sitting in the feed device on the dish, right outside of it where the cable's mounted. Because that way you don't pick up any loss of the cables, like in that previous example with the 6 dB that you can't make up. So right off the dish, right in the feed device. That's where the low noise amplifier or low noise block converter is located. And what the block converter is about is it takes high frequencies from the satellite and it breaks them down into a low frequency range, which the RG6 cable, which is typically used in cable TV in a house, can handle without a huge amount of attenuation. Okay, effects of noise on digital circuits. So we have 3 strategies here, and the first is to ignore it. Now when you talk out of your local exchange on a regular telephone line, there's no error correction, and it's digital signal subject to noise. And if you get a click or a pop, you pay no attention to it, or if it's really distracting, you can ask the person to repeat themselves, and that would be a form of a retransmission. But in the telephone network, not cellular, but in the regular POTS, plain old telephone service network, one of the strategies is to ignore noise. Second, we can detect noise. We can find out, hopefully, if we've got a packet that's an arrangement of bits with a header and a tailer. What that does is it takes a large file and breaks it up into manageable chunks. And there's reasons for having large and small packet sizes. And the trailer here contains information that not only says if the packet is aired, but also says I'm the end of the packet. So your receiver will know that. So we have the option with detecting errors sometimes to retransmit them, the packet. So if you download a file over the internet, you can certainly do that, but if you're receiving a digital broadcast from your television set, it's kind of hard to say stop what you're doing and resend the packet, because the last picture I received had a noise blotch in the corner. So television transmission has to use a different way of mitigating errors. So if we take a look at the transfer data in the TCP protocol, so we have the sender, and I'm showing this sending to the right here. This is packet 1, 2, and 3, and the data are broken down into packets, have numbers, 1, 2, and 3, and then the sender of the packet treats it like a very large binary number. So it's taking all of the data bits in the packet and looking at it as a concatenation of binary numbers. And then the sender and the receiver over here have to agree on a divisor. So they have to come up and negotiate and figure out what kind of number they're going to divide this great big number by, and this will make sense in a second. And then after the data are transmitted, the sender appends the remainder of the division process to the back of the packet. It's indicated here by these little red lines. And then the receiver receives the data and divides it, treating it again as a great big binary number, by the same divisor. And if the remainder, which has been appended, is the same at the receiving end as calculated of that of the packet that's coming in, it's very likely that there aren't any errors. So this is called cyclic redundancy check, and it's a very powerful error detection tool. Now, if the CRCs do not match, if these remainders do not match, there's a very high probability of an error. And then in the TCP protocol is that there would be a request for transmission for that damaged packet. So let's look at an example here of cyclic redundancy check, and we're going to let our data be G as a function of X, and it's just this little binary here. And our CRC is going to be P of X, and the equation for that is X squared plus X raised to the 0 power, which ends up being 101, number 5. Now CRCs can be 16 bits, 12 bits, 32 bits, so there's a lot of different names of these. So we're just making one up here, a very simple one, so we can kind of explain this. So what we're going to do is a long division problem here, and this is my data load, and I'm going to divide it by 5, and in so doing you can just see the process of long division here, and this is the quotient, and we're going to throw that out. It's not going to be important to us. And then when we get over here is what we'll see is that we have to add a couple of zeros to make up for this, and what happens is that the CRC itself is 1 bit less than the divisor. So we keep going until we get a cyclic redundancy check here. In this case, this is 0, 1. That's our CRC. So if we were going to send this packet, this time I'm sending it this way just to be confusing, MSB first, if you will, and the packet goes out, and then appended to it is the remainder of that division. And then the receiver would be doing the same division and check his remainder with our guy that he receives. There are other ways of finding errors, block check characters, and so forth. The CRC is very powerful. Now, if we did that one packet at a time, it would be called a stop and wait prototype. Send a byte along to your receiver. Receiver looks at it, figures out if it's good, and then sends you an ACK, acknowledge, got it, or a NAC, no, bad. But the stop and wait protocol would take a long time because of the ping-ponging of the traffic. So what the sender does using a sliding window protocol, it just launches a whole bunch of packets. 1, 2, 3, 4, 5, and this is the window. Now the receiver gets one OK and sends an ACK back. Number 2, it picked up an error, so it sent a NAC back, negative acknowledge. Number 3 came in OK, number 4 came in OK, and well, number 5 was lost in transmission. Now that means that this could have been mangled so badly that you couldn't even identify it as a packet coming from the source. But it would be contained in the header information. So the sender guy here gets the NAC back for packet number 2, and then he'll resend packet number 2. Now, with regard to packet number 5, the receiver doesn't do anything. He doesn't even know what he got. So the sender is waiting for an ACK or a NAC and times out. And a timeout means that he's going to relaunch packet number 5. The receiver, say, gets it OK and acknowledges 5. So between the ACKs, NACs, and timeouts, it's a pretty robust protocol. So packets can arrive at the receiver out of sequence, because some packets may be taking this path, and some packets may be taking that path based on network congestion. So the sender has to buffer all these packets, that is, keep them active until it receives an ACK. We can clear out his buffer space because he may have to send it again. The receiver may have to assemble the packets that don't arrive in the correct order. Larger packets saves time if the error rate is good. Otherwise, you have to resend a large packet. So smaller packets saves time for higher error rates. So there's a lot of trade-offs that go into this, and this is a protocol that sits under the hood of TCP. Now let's talk about our off-the-air television arrangement again here, and also used with CDs, is called forward error correction. And detecting an error just isn't good enough, because in the CD, what are you going to do? Say, okay, you got some bad music here, and there's nothing to resend, it's just damaged. And in television also, the movie goes on, so to speak. So in this case, we're going to take 7-bit data packets, and this would be these guys here. I call them 1, 2, and 3. And what we're going to do is assign a parity in the horizontal and vertical dimensions. Now, what parity means is that we agreed upon an even or an odd parity, which means the entire line, including the parity bit, is going to be even or odd. So parity is a very common and simple error detection, and it can detect 1 bit. Anything more than that, perhaps not. So we agree on even parity here, so let's see how we do that. I'm going to start off here. This is 1, 1, so odd, even, odd, even, odd. To make it even, I need a 1 in a parity bit. Second guy, odd, even, all is well, 0 in a parity bit. Third guy, odd, even, odd, even, odd. Need a 1 in a parity bit to make it even. And then we do the same thing in this direction. Odd, even, good, 0. Odd, need a 1. Odd, even, even. And we keep doing that right across the entire horizontal dimension of our 7-bit data packets. So what happens here then is that sending the information would send out data number 1, data number 2, data number 3, and then our horizontal and vertical parity. Now, how does this fix bits? Well, let us say we get an error here in this bit. That means that this parity bit is going to be wrong. This 1 is now a 0. And that also means that this parity bit is going to be wrong. So the intersection of the parity bits zeroes in on the defective bit, and all we have to do is toggle that and we fix the problem. Now, it's also possible that we get an error in one of the parity bits. And the reason we know it's a parity bit that got the error is the other parity sequence would be correct. So if we have an error in a parity bit, we do nothing. Now this is good for correcting single bit errors. There are much more powerful algorithms, but the nice part about this is it's very easy to see. Next topic is the interleaving, and this occurs on CDs. And CD has 2 16-bit linear pulse code modulated tracks that make for the stereo, and is sampled for commercial use at 41,000 bits per second, or more correctly, samples per second. And here we got a scratch. And when these were designed, these were the smallest man-made features on the planet. So what our scratch can do is it can mess up multiple bits in our 16-bit words, and FEC, forward error correction, which is used here, won't be able to fix it. So by interleaving, what we're going to do is be taking, in the example I have here, 4 samples in different colors, and we're going to be sending bit 0 of this sample, bit 0 of this sample, bit 0 of this sample, bit 0 of this, and then we're going to interleave. Well, these 3 are interleaved with the first bit. And the same with bit number 1 and bit number 2 and bit number 3. So, here's our great big scratch guy that just took out 4 bits. Now, if that 4 bits were involved in one 16-bit word, forget it. Not going to fix it. But if it's spread across 4 different words, FEC has 1 bit error per word to fix, and it can do it. So interleaving is a very powerful method. It's used based on the fact that errors often occur because the surface is defective, and a scratch is really wide compared to the number of bits that it will get. Now, one last thing, noise in a PC layout, just wanted to mention this, is this is our power supply ground, and we've committed a bit of a sin here as we're mixing digital and analog logic. We have an op amp, and I've got it connected to 4.2 volts, which is open, fully charged voltage for a lithium-ion battery, and we're going to be wanting to amplify something for some reason, and we also have some digital electronics in here also. So for that, I've shown an inverter. Now these are CMOS, and when they switch, they typically have a little pulse of through current where both the pull-up and pull-down transistors are momentarily turned on. And that current is shown kind of down here is what that would look like. Now PC traces are horrible conductors. There's more wrong with PC traces than you can imagine. Crosstalk, dielectric absorption, inductive components, resistive components, bad. So what we can say here is the voltage drop across this trace is going to be caused by I times Z1. So here we've got the pulse of current coming in here, and what happens where our op-amp ground node connects into the ground is that this is also going to bounce. Well, if we apply an audio signal here and this is constant, as the audio voltage changes, it's going to be amplified by the amplifier. Now, if we don't have an audio voltage and we take the ground and push it up, it's the same as taking the input and pushing it down. It thinks that this bounce here is signal, and therefore the output of this here is noisy. So when you lay these out, and PC boards with noise like this, is the correct way to do that would be to return this to the star ground, and this point here, which would be the bias point, 50% point, and if you've had electronics 1, that would be the ground potential because you're negative and positive. Also has to be very clean. So this is a very common source of noise voltage in PC layouts, is this sort of thing, referred to as a ground loop. Not good. So with that I'll conclude, and thank you for watching.